Hello and welcome to New Planet School. Let's do some trigonometry, and specifically let's look at some trigonometric functions, the sine, the cosine, and tangent, the basic three functions that form the heart of trigonometry. We'll start off by talking about why we would want to do this and what leads us to the trigonometric functions. What are the applications we'd care about, and what are the questions that we might want to have? Once we've set that up, we can go directly to the definitions of the trigonometric functions, connect them to the unit circle, and talk about some of the mathematical properties of these functions and some of the graphical properties of these functions, so we can have a picture and an intuition for what these functions look like. So this is our basic program for this video. Okay, so why? Well, imagine you're a geologist and you're doing surveying and you want to know how the continents are moving around, so you can know something about the properties of the Earth. Or, for example, suppose you're doing drug design, you're a biochemist, and you want to understand the relationships between the bond angles in this molecule to design a better drug to help people. All of these types of problems, as different as they are, can all be boiled down to looking at polygons with three sides, which are triangles. So all of these problems have this in common, and this is why we want to study this particular shape. Okay, now what we want to do in practice is we want to do what's called solve the triangle, and what that means is the following. In a triangle, there are 6 pieces of information, and we might want to know what all of those things are. So what are those 6 pieces of information? Suppose we have a side here and an angle here, side here and an angle here. We're up to 4. Here's a side and here's an angle, and now we're up to 6 pieces of information. Clearly, if we had all 6 pieces of information, we knew everything we need to know about this triangle, and we can use it to solve whatever the problem is we're trying to solve. Now, what trigonometry tells us is something very interesting, and that is that we really only need 3 pieces of information to start with, provided that 2 things are true. One, we need to know at least one side. In other words, if we only know angles, like this, say this has angle B, C, and A, it's similar to this triangle, but it's not the same as that triangle, so we can't figure out what the sides are. We need something that tells us the sense of scale, and that's why we need to know at least one side. The other thing is we have to make sure that the information actually allows for a solution. So, for example, if someone tells us you have a triangle and A plus B equals 190 degrees, clearly you don't have a real solution, because you know that the sum of the angles in a triangle have to all add up to 180 degrees, and this would simply be too much. So as long as you know for sure you have a triangle, you have 3 pieces of information, and one of them is a side, you can figure out all 6 pieces of information. Okay, so let's think about how that information might get to you. When you do homework problems, or you have a problem in real life, information often comes in very different ways, and so let's talk about how it might get to you. One way that it might get to you is someone might give you 3 sides. So imagine you have a triangle, and someone gives you the length of this side, the length of this side, and the length of this side, and your goal is to find these angles. Well, you can do that. That's a perfectly legitimate problem. You probably have a homework problem on that at some point. Now, not all 3 sides will make a triangle, as I show here. These 3 sides don't make a triangle, and so there are cases where the SSS doesn't make a triangle, but if you know you have one, you're home free. Okay, another possibility that you have here is angle side angle. So imagine someone gives you an angle, I'll call that A, and they give you a side, I'll call that S, and they give you another angle, I'll call that A prime. And so you have an angle side angle. Sometimes that makes a triangle, and sometimes it doesn't. If you know you have a triangle, for example, if this angle were right here instead, then you'd have a legitimate triangle, and you could figure out the remaining pieces of information from that. And that's another type of problem. Okay, now there's also side angle side, and this one I put in green, and the ordering here, side angle side, is important. This one's a nice one because if someone gives you a side and there's an angle between that and some other side, that's why it's side angle side, because it's an angle between two sides, then you can figure out the rest of the information. And in fact, you always can do this for this case, because if I know where this point is, and I know where this point is, because I know these lengths of these edges, I can always just draw a line between them. I will always get a nice triangle, and I can go get the remaining information that I need. I can always do that. So I put that one in green. Okay, now suppose I wasn't given the information in that order. So for example, suppose someone gives me a side. They give me another side. They don't give me this angle, but they give me an angle somewhere else, sort of over here. I get an angle over here. Well, sometimes that works and sometimes that doesn't. When it does work, I can always go like this. I'm given this angle, and with a side, side, and one angle, I can then go get the rest of the information. So that's the way the information might actually get to us. And when you're solving homework problems or problems in real life, you have to sort of get used to how these things come at you and learn how to solve them. Okay, so almost never when you're learning trigonometry, even using trigonometry, do you actually look at triangles that look like that. They often come to you in a real life problem like that, but when you actually sit down to analyze them, what you usually will do is you'll take this triangle that has some odd shape, and what you'll do is you'll break it up into two triangles, and you're going to put a little box like this. This is called a right angle because it's 90 degrees, and this line that comes down is called the altitude, and it hits this bottom right here, which is called the base. And what that does is it breaks the triangle up into two right triangles. So here's a right triangle, and here's a right triangle, and you can always do this. And therefore, when you're doing trigonometry, you often will spend most of your time studying right triangles, not these arbitrary triangles. Now, of course, if you can solve a right triangle, you can obviously solve another right triangle, and you can put them together and get the rules for the overall triangle. But in general, you start off with trying to do things for right triangles. So when we define our trigonometric function, we tend to do it for the right triangles because that's really the place to start. Okay, so let's get with our definitions. Let's define our trigonometric functions. It's time. Okay, so we have our right triangle. This is what we're going to be doing, is spending a lot of time with right triangles. So I'll put this little box down here. That is our right angle. It proves we have a right triangle. Now, when you have a right triangle, there's these special names. The side that's across from it, I'm going to call H, and that has a special name called the hypotenuse. And that's the side across from the right angle. Now, if I choose this to be my angle over here, which I'll call theta, there's another special name. If you zoom all the way across over here, this is called the side O, which stands for opposite. And the other piece of information, a new name, the one that's on the side here, we'll call that to have length A because that is the adjacent side. Now, here's something interesting. If you look at this triangle, what you realize is you can't solve it. It's not possible to solve this. We have a right triangle, we've labeled everything, but we can't solve it. Why can't we solve it? The reason we can't solve it is what information do we have? We have one piece of information here, which is an angle. We have another piece of information here, which is an angle. So we have angle, angle, and we don't know anything else. We don't know the length of these sides. We don't know the length of these sides, and we don't know this angle yet. Okay, so what are we going to do? One thing we could do, obviously, is we could figure out what this angle is, because we know that the sum of the angles of in a triangle are 180. So we could figure out what this angle is, and that would give us an angle-angle-angle relation. But remember, that's not enough information, because we need a side. So we can't really solve this triangle yet. We really don't have enough information. We don't have any of the sides. Now, the consequence of that is the following. Suppose I draw a right triangle like this, right? And I have the same angle here. So two of these angles, actually all three of these angles will be the same, and this triangle is similar to this one, but I cannot figure out the lengths of the sides because I simply cannot get around this fact that I need a side. So how are we going to relate these angles to these sides? Well, here's the key insight that leads to the trigonometric functions, and it's this, is that this length along this adjacent side, as it gets longer, say it gets to be this long, it will grow in proportion, for example, to the length of the hypotenuse, which is this length. And they'll scale together, as will the opposite length will also scale. And so what that means is that the ratios of these lengths stay the same. So it makes sense to talk about these ratios. So which ratios should we talk about? Okay, well, let's imagine we have a ratio of the opposite side to the hypotenuse. And as we scale this up, this is a reasonable property of the triangle. The ratio actually has some meaning. Another ratio I could consider is, for example, the adjacent over the hypotenuse. That's a reasonable ratio, and that's all I can specify. I'll never get an actual length. And then I might as well come up with one that doesn't have the hypotenuse in it. So let's do opposite over adjacent. And these are the ratios that are common between all these similar triangles for right triangles. And what I'm going to do is I'm going to relate the angle, which is what was a given, to these ratios. And I'm just going to define these functions. I'm just simply going to define them. And what I'm going to say is there's a function that's called sine, and I'm going to write it with sin theta. Sine of theta is equal to the opposite over the hypotenuse. So if I knew what this sine function was, like it's in my calculator or I have a table or something, you give me the angle, I take the sine, and I can get this ratio. Again, I can't get an actual length because I don't have enough information. I'm going to define another function called the cosine, which I will write just cos of theta, and that is going to be equal to adjacent over hypotenuse. And then I will define a third function called tangent, which I'll abbreviate tan of theta, and that equals opposite over adjacent. So you give me theta, I can take the tangent, and that will give me the ratio of this side to this side. And if you give me theta, I can take the cosine and get the ratio of this side to this side, and the same for the sine. So here's what's neat. If somebody were to give me a side, like say you told me the hypotenuse was equal to, say, 1. If I knew the hypotenuse was 1, then if you give me the angle, I know absolutely what the adjacent is. If I know absolutely what the adjacent is, I then know what this number is. I know what tangent theta is. I can figure out the length of the opposite side. So as soon as I'm given one side, I'm done. I can figure everything out. But with these trigonometric functions, I really can only get these ratios. I can only get these ratios. And these are the important ratios. And these are the definitions of the trig functions: sine, cosine, and tangent. Okay, now we have our definitions. Now, you might be wondering, why is it that I defined them that way? I could have very easily taken my right triangle. I could have put my angle over here. This is the opposite, this is the adjacent, this is the hypotenuse. And I could have said, well, I want to relate these. Why don't I, instead of doing what I did before, opposite over hypotenuse, I can do hypotenuse over opposite. Or I can do hypotenuse over adjacent. Or I can do adjacent over opposite. This is just 1 over the other relationships that I had. And why isn't this just as good? Why isn't it better? In fact, it is just as good because, like I said, you can only get the ratios anyway. You can define them this way if you want. And in fact, people do, and these functions also have names. And this first one right here is called cosecant, and it is abbreviated CSC of theta. So you can use that if you wish. This one is just called the secant, abbreviated SEC. And then there's the cotangent, which is COT of theta. And if you want, these are perfectly legitimate functions that you can also use if you prefer to use these functions. Cosecant, secant, they do just the same job as the other functions, and you're welcome to use those if you wish. I'll show you later why you might not want to use these and why they're less common. But I felt it's really important to mention it. You might come across it. You might have some homework problems where you have to do some of these things. And just remember, these relationships. Cosecant is 1 over sine. Secant is 1 over cosine. And cotangent is 1 over tangent. They're interchangeable, and you can do whatever you want with them. Okay, now, how are you going to remember these relationships? Well, here's a mnemonic that's very popular. A lot of people like to use this. It's called SOHCAHTOA, and who can't remember SOHCAHTOA? That should be an easy thing for you to remember, right? It has a kind of a funny name. And so here's the way this works. It basically tells you what the trigonometric function is and what the ratio is that you want. So here we have sine is opposite over hypotenuse. And this is cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if you can remember SOHCAHTOA and write it down, it gives you the trig function and the ratio. The trig function and the ratio. The trig function and the ratio. So SOHCAHTOA, commit it to memory, and you'll remember the trigonometric relations. Okay, now I wanted to say a little bit about slope, just to relate this to something physical that you can think about in the real world. Suppose you have a triangle like this, and this line right here that goes like this has some slope. Maybe this is a road, there's a car, you're driving your car, got your car driving down here, there's some slope, and you want to be able to relate the slope, which is something you think about in everyday life, to the trig functions, which in particular relates to this angle. Well, the slope, of course, has a definition. It's equal to the rise over the run. Well, this is the rise, and this is the run, and so that's very obvious. So now what we can do is we also know that tangent of theta is equal to, what is it? The opposite over the adjacent. Opposite over adjacent. That's the TOA part of SOHCAHTOA. And of course the rise is just that length of that side. and the adjacent is the run, and therefore we see that the slope is equal to tangent theta. And therefore, tangent theta has a physical meaning that you can relate to everyday life. Because the sine of the angle is related to opposite, the sine is kind of like the rise part, and the cosine is sort of like the run part. But in general, keep in mind that tangent theta gives you slopes. Okay, now I also want to relate this to the unit circle. This is a unit circle. It's a circle with unit radius. That's why it's called the unit circle. And you can see that the distance to any point on here is equal to 1. So how do we relate this circle to a triangle? What we do is as we want to do, we make a right triangle, because that is always the game in trigonometry. Make a right triangle somewhere. And what we care about is this angle right here, so let's label it as theta. And now the circle problem looks exactly like the trigonometry problem, and therefore we can quickly do many things, like what is this point here, xy? What is that? Well, let's use trigonometry. We're ready to go. We know that this side here, which is opposite, of course, the length of this side is just y. So that equals y. And we know sine theta now from SOHCAHTOA is opposite over hypotenuse, but the hypotenuse in this case is 1. So this is just O, which is just equal to y. So the height here is equal to sine theta. Similarly, cosine theta is adjacent over hypotenuse, but that's equal to 1. So that's just the adjacent. Well, the length of the adjacent side is x. So x equals cosine theta. So if you ask yourself, where is this point? It is at cosine theta, sine theta. You give me theta, and I'll tell you exactly where this point is. And if you give me a different angle, I can tell you where all the points are along this unit circle. And when you study the unit circle, and there's another New Planet School video out there, you'll be able to figure out what all these other points are as you go around in the unit circle. So you might want to go watch that video. I just wanted to make a connection to the unit circle here. Now that I've defined the trigonometric functions, we can make that connection. Okay. Now, Pythagorean theorem, another really important fact in trigonometry is the following. Suppose we have a right triangle, because as I said, that's mainly what we're going to be doing. We have a right triangle, and it has, I'm going to label this A, B, C to make it arbitrary. What Pythagoras showed is that the length of the sum of the lengths, the sum of the squares of the length of the sides equals the length of the hypotenuse squared. Therefore, a squared plus b squared equals c squared. That's the Pythagorean theorem for a right triangle. Similarly, if you have a triangle that satisfies this, you have a right triangle. So that's what Pythagoras told us. Well, what does this have to do with trigonometric functions and circles? Well, it's very interesting what we can do with this. Watch this. Just watch this. Again, I come over here. I make a right triangle because that's what I know how to do. And I say, wait, I have a right triangle. Therefore, this triangle is subject to the Pythagorean theorem, must apply. So let's write this as y, and this as x, and this is the point xy. And what would Pythagoras tell us about this? You know, while we're at it, we might as well find out what he would say. What he would say is x squared plus y squared equals the hypotenuse squared, which is 1. Right? So this is what Pythagoras would say about any point on the unit circle. But watch what we can do. Remember what we just derived? We also just derived that x equals cosine theta, just from the definition of what cosine theta is, and y equals sine theta from the definition of sine, using SOHCAHTOA or however you want to remember it. So let's put these two things together, and we find this truly amazing relationship by just sticking this in there. we get sine squared theta plus cosine squared theta equals 1. And this is a very important identity in trigonometry that falls out very easily once you realize the definitions of sine and cosine connected with the Pythagorean theorem lead to this, and the derivation is quite simple and very easy to understand. So I wanted to also make that connection. Okay, now let's talk about some properties of these functions, just so we can know why they're easy to use or not so easy to use, or if we get a number out of our calculator, we know that it's right or it's wrong or it's possible or not possible. So let's think about that. So again, what do? We draw a right triangle. We have our right triangle, and we know that this height y equals sine theta, and this x equals cosine theta, and this point on this unit circle is x, y. Okay, pretty much established that. But let's notice something. If this is the angle down here, what are the possible values of the angle? The angle can go up here to 90 degrees. It can go around and around. There's no limit how far it can go. And also, by the way, there's no reason the angle can't go the other way. I can also do an angle this way that could be negative, and I can go backwards around this way. So what that says is that the domain of these functions, it can go from minus infinity to infinity. There's nowhere along this axis where things don't make sense. Okay, now let's focus a little bit on the sine, since I already have that written here. Suppose that this angle were really shallow, so it went like this. This height right here is pretty small, and as I move around, it gets longer, and eventually, if I have a triangle like this height right here is almost approaching 1, and as the angle goes right up to 90 degrees, it's actually equal to 1. So what that suggests is that this function starts at 0 when theta is 0. That's this really small height, and it goes up to 1. So it goes up until it hits 1. And then it turns around, and it starts getting smaller again. These y values here start to get smaller and smaller. So once it gets up to 1, it turns around until it goes back to 0 again. And then I go over here, and my y values are actually negative until I get to minus 1, and then they get bigger again until it comes back to 0. So this looks like this. Now what if I had gone back the other way? I would have gotten a function that looked like that. But one of the things that you see is this function can never be greater than 1, and it can never be less than minus 1. So it can exist for any theta, but it can't be greater than 1 or less than minus 1. That's called the codomain. The other thing that we see about this function is that it's odd. And what does it mean? Do you remember what it means to have an odd function? What it means is any function that's odd has f of x equals minus f of minus x. And so sine theta equals minus sine of minus theta. So let's look at that. If we look over here, as we go here, if I go all the way over here, that's minus theta, and I get a value, which is minus 1, and then I put a minus sign in front of it, I should get the same thing at the same theta over here, which is plus 1. And so that's an odd function. And you should, just as an exercise to yourself, work through these two ideas for cosine and for tangent to make sure that you fully understand this. I won't do it so that you can have that as a nice homework problem for you to work through. You can watch this part of the video again and then do it along with it and do cosine and tangent. Because I want to tell you something else, which is this. This actually kind of shows us why we don't like to do the other trigonometric functions. Suppose I want to look at the cosecant. Okay, so I'm going to do the cosecant instead. Okay, now what happens here? What's going to happen here is this. Instead of doing this height divided by the hypotenuse, because remember sine is opposite over hypotenuse, I'm going to do hypotenuse over opposite. But when the opposite, which is this height right here, becomes really small, this thing becomes really big. And so what will happen is it will actually go to infinity. And then as it goes up, it will come down, and then the height again, they'll be equal again, it'll come down to 1 and go back up. So it comes down from infinity, and then it comes down to 1, and then it turns around and goes back up to infinity. So it has this very bad behavior. And so even though it's a perfectly useful function, this is one of the reasons that a lot of people don't really like to use it, is it has its codomain. It's the opposite. It can't exist in here where things are nice. It only exists out here where things are going to infinity. So I think this is the reason that a lot of people don't like to use cosecant, secant, and cotangent, and they prefer to use sine, cosine, and tangent. They're just better behaved, and you can easily see that by looking at the properties that come out of this unit circle. Okay, so here's some actual pretty graphs instead of my graphs. I wanted you to see what these actually look like. And so just quickly, here's the sine function here. This is sine theta, and I'm plotting this from minus 2 pi to 2 pi. Here's 0. Here's the origin. It's an odd function. It exists between minus 1 and 1, just like I said. And here is the cosecant of theta, and again it exists up here and down here, and it goes up to infinity here, and it goes down to minus infinity here. And so not very well behaved, but that's what these functions tend to look like. Again, you can use cosecant. It has the same information in it. It's just a little bit messier to deal with. Okay, same thing for cosine. Here is the cosine function, and here is its inverse, the secant, which is just 1 over cosine. That's what I mean by inverse here. And again, it sort of badly behaved. These things are going up to infinity up here, and they're going to minus infinity down here. Not very nice to deal with. A little bit nicer just to deal with functions that are nicely behaved and they stay inside here. So that's what those two look like. Okay, the tangent always has a very strange behavior. This is the tangent function right here. It goes up to infinity here, and it goes to minus infinity here. That's tangent of theta. And then this other, the green one here, is cotangent of theta. And here, things are coming from infinity going to minus infinity as well. And the reason, of course, that you can't really fix that is because tangent of theta is, if you work through it, you notice is sine theta over cosine theta, which you can work out from SOHCAHTOA or however you want to remember it. But because cosine will sometimes go to 0, it will cause the tangent to sometimes go to infinity. And you can say, well, I want to get rid of the infinity, so I'm going to use the cotangent, which is 1 over that. I could do that, and that would give me cosine theta over sine of theta. But the problem is sometimes sine goes to infinity, and so you can't really fix it. And that's why the green curve and the blue curve both go to infinity, and they have these shapes. So now you have a pretty visual image. Now let's see how these are connected to the unit circle, to see as we go around the unit circle how the height, the y value, and the base length, the x value, generate the sine, cosine, and the ratio makes the tangent. So here I made a little animation just to show you as you go around the circle how the sine goes positive and negative depending on which quadrant of the unit circle I happen to be in. And here on the tangent function, I drew these vertical lines so you could actually see these asymptotes right here where it's going to infinity. Those aren't actual values. That's just showing you where it's not defined, in fact. So, okay, now here's something that I wanted to show you right before we finish. And this is something that very few people know about. It's probably not going to be in your textbook, and your teacher's not going to teach you this, but I wanted you to see it so that you could have, really deep insight into trigonometry that most people don't have. And it's really interesting for the following reason. When we started talking about in the beginning of this video why we would want to do trigonometry, and that means we're going to deal with applications that have angles in them, and we have triangles, and we're going to break that down into right angles, and we define the relationships between the sides and the angles in terms of the trigonometric functions, and then we connected that with a circle through the unit circle. Now I'm going to define the trigonometric functions with no reference to trigonometry or triangles and no reference to a circle. And this is something that's extremely interesting, extremely powerful, and used every single day by scientists and engineers. No triangles, no circles. This is really interesting. Okay, so what I want you to do is think about this sine curve. I have 4 curves: sine, cosine, minus sine, and minus cosine. Now if we look at this curve, they're not lines. They're these wiggly sinusoidal periodic functions. They just keep on going in both directions. So it doesn't really make sense to talk about the slope like I talk about the slope of a line, but you can imagine talking about a line that would actually be tangent to a point on this curve. And right here we would say that only at this one point the slope is 0. Same thing here, there's a slope of 0. Same thing here, that only at that point there's slope is 0. Here the slope is 0. The other thing I can notice is that here you can see the slope is about 1, and then like right here the slope is a little bit less, maybe a half, but the slope is always positive. Same thing over here. The slope is changing, but it's negative, and here the slope is positive, the slopes, and then here the slopes are negative. It's changing, so it's going positive to 0, negative slopes, 0, and so forth. Now here's what's really interesting. Take a look at this. If the slope here is 1, what if I plot that? Well, here's 1. Here the slope is 0. What if I plot that? I get a 0. Here all the slopes are negative, so I'll put a curve here that is negative. And here the slope is 0. I'll plot that. While I'm at it, I'll plot here and I'll plot here. These slopes are negative. These slopes are positive. And what you see is the cosine function is telling me what the slopes are of the sine function. That is truly amazing. Now, if I continue this line of reasoning, watch what happens. If I do the same thing for the cosine curve, this has a slope of 0 and negative. 0, negative function. It's all negative. And then when it gets here again, 0 slope on here. Here's a 0 slope, 0 value. Here's a 0 slope, 0 value. And the same thing. Here we have positive slopes, and here minus sine, notice that's what this is always positive. So what we see is minus sine is always giving us the slopes of the cosine curve. That is amazing. So isn't this interesting? If I do this twice, I take a curve, I find its slopes. From that curve I find its slopes, and if it gives me minus my original function, then that function must be the sine. In other words, the sine function is the function that if I find all of its slopes 2 times, I get minus that function back. And that is a way to define the sine function which has nothing to do with triangles, nothing to do with circles, nothing to do with trigonometry. It has only to do with the properties of the curves themselves. And so I mention this because a lot of the applications in the real world for trigonometry use this definition far more than they do the other definitions. For example, if you look at the frequencies of the notes in music or the colors of the rainbow, these different frequencies we tend to think of as these oscillating curves that have precisely these properties between the slopes. So when somebody's analyzing music or color and light, you often aren't using triangles or circles, you're using this particular property. So this is something you're not going to see very many places, but I hope you found this part particularly interesting. Okay, so summary. We started off by talking about some applications of trigonometry and pointed out that we can solve the triangle that results from those applications if three properties are given, as long as it is a length or a side, and it has to be something that's possible. And that's really how trigonometry works. You have a problem, you relate it to a triangle, you are given some properties, and you solve for the remaining properties. That's what you really want to do. Now, we typically will break that down into a right triangle, and so we typically will always be working with those. When we do that, it allows us to define the basic three trigonometric functions, sine, cosine, and tangent, which relate the angles to specific ratios of sides. There are other trigonometric functions, cosecant, secant, and cotangent. You're welcome to use those. You might have homework problems. You may come across those. They're completely equivalent. They're just one over the other functions, but they're not so well behaved, and so often people don't like to use those. We also related things to a circle, and that allowed us to do something amazingly powerful, which is to use the Pythagorean theorem to prove an amazing relationship that's always true for any angle. And that was a really neat outcome of that. And then I showed you something that's not in most of the textbooks, that these trigonometric functions can be related to the varying slope along a smooth curve. And so that was a completely new and different way of defining these functions. And later on, if you continue with math, you will see that again and again. Okay, now what should you do? You should take this quiz. I won't go through all of these questions and ideas, but pause the video, go through these very carefully. As always, it's an open video. This is for your benefit. This is for you to learn. This is all for you. And see if you can answer these questions. Rewatch the video if you need to. Make sure that you understand all of these ideas and some of the other ones, and you'll be on your way. All right. Finally, with that, I hope to see you here at New Planet School very soon.